Hello everyone, I am Karam Samir Qasim Kassab, a faculty member at the Northern Technical University and one of the authors of this scientific paper. Our paper is developed about identifying electrical issues by Cascade Bayesian Regularization Neural Network (CBRNN). Effective detection of electrical power grid faults is essential for ensuring system reliability and longevity. As the power demand grows, artificial neural networks offer promising solutions for recognizing complex patterns. This paper introduces the Cascade Bayesian Regularization Neural Network to detect or diagnose electrical faults using data from Google's Electrical Fault Detection and Classification dataset. Inputs include ground, phases, current and voltage, with a mean square error MCE of 0.0219. The Cascade Bayesian Regularization Neural Network demonstrates high accuracy in fault detection, minimizing dispersion and financial losses. The rapid expansion of electrical power infrastructure requires constant, stable, and reliable power sources. However, with the growth of interconnected systems, early fault detection and diagnosis is critical for maintaining power stability. Traditional algorithms often lead to delay and inaccurate fault detection. Artificial neural networks, widely used in energy systems, offer a powerful artificial intelligence based approach for pattern recognition, fault identification, and diagnosis. By mimicking biological neurons, artificial neural networks provide effective solutions for ensuring early fault detection and diagnosis, enhancing system reliability, and minimizing disruption. This field has seen extensive research and development in recent years. Actually, this paper aims to identifying electrical issues for operational state and fault. It proposes the Cascade Bayesian Regularization Neural Network for energy infrastructure, safeguarding or protecting. It also highlights its potential to effectively analyze data and identify normal operational state and fault with high accuracy. First of all, as we see, we have two figures. Figure 1 represents concentrated electrical circuit, and this figure contains four generators. Every one of them generate 11 kilovoltage, and all of them are connected to two transformers with three-phase turn ratio at either end of the model's three-phase power system. In addition, a 300 kilometer and 50 Hz transmission line with a wide resistance and faults are available in the ceiling of MATLAB. This allows MATLAB to evaluate transmission line faults. The design formed a virtual network as a ring system to provide continuous power flow through power transmission line to consumers or to users. Additionally, the model is considered close to reality, so it's worth to exploit this model. In the figure 2, the proposed Cascade Bayesian Organization neural network where the line, currents, and voltage are the inputs and phases A, B, C, G are the output. Actually, to identify electrical issues of normal state and faults, the CBRNN is proposed. It's a multiple layer neural network. It employs the lines, currents, and voltage as inputs in its input layer. Furthermore, it exploits the ground and phases for the outputs in its output layer. It also has one hidden layer between input and output layers. With a more detailed explanation, Bayesian localization neural networks enhance the performance of the cascade forward neural network. This is due to its ability in the case of providing smooth or regular outputs. Such a specific advantage strengthen the CBRNN model compared to traditional methods, which cannot produce smooth or regular outputs. Bayesian regularization reduces the linear combination of squared errors. It integrates prior parameter information, limits overfitting, and minimizes parameters variances. It integrates prior distribution for parameters based on pre-data beliefs. Theorem updates the parameters predictions, creating a posterior distribution that integrates previous knowledge with available information. Generally, employ Bayes' theorem to integrate prior knowledge with actual data to obtain more estimated results and generalized parameter. Essentially, Bayesian regularization minimizes parameter variances and enhances generalizability of a neural networks in its training phase regardless of performance of the testing phase. As we see in the figure 4, shows Bayesian interface fundamental block diagram. Bayesian interface, which is used for pattern and population learning and classification, is demonstrated in the field of science. The following example uses two blocks to apply Bayes rule for estimating model parameters and changing density function using random weights in the Bayesian network. Also here we have equation 22. This equation represents P, where P is the function of density, D is the data set of input, beta and alpha are the parameters of an objective function, M is the applied neural network model, and VW is for the vector of the network weights. As I mentioned, the Cascade Bayesian regularization neural network is proposed in this work. It's considered detecting electrical faults for the electrical circuit, which is shown in figure 1. Fundamentally, all line voltage and currents are recorded for every failure. CBRNN fault identification is based on the codes of 0 and 1, indicating faults on the electrical line of line A, line B, line C, or ground. Table 1 provides the normal state and faults for the concentrated circuit. Codes of normal state and faults in the table are used as the output layers of our proposed CBRNN. Each code of 1 refers to a fault in an electrical line, whilst each code of 0 refers to a non-fault in an electrical line. Such codes are used as a target in the training phase and expected targets in the testing phase. Number of inputs in the CBRNN input layer equal to 6, where each input refers to a line voltage or current as I mentioned. So, any CBRNN input except a voltage or current line value. Also, a more complex input-output relationship is implemented. The power of training and testing algorithms of the proposed CBRNN can efficiently establish their relationship. A big number of the value are exploited. That is the number of the training cases is 3,931 samples and the number of testing cases is 3,930 samples. However, number of hidden nodes in the CBRNN hidden layer that is applied here as 100 neurons. The transfer function that have been used in the proposed CBRNN are sigmoid and linear in the hidden layer and output layer respectively. For the training phase, the results seem so valuably. Firstly, for enhancing the reproducibility and provide insight into the training dynamics, the hyperparameters of learning rate Number of hidden nodes and number of epochs have been appropriately selected during the training process. That is, the learning rate is automatically optimized the Bayesian regularization, whilst the number of hidden nodes and number of epoch are experimentally selected equal to 100 and 500 equally. From the figure can be seen that the training phases has attained significant performance. To use the training curve has dramatically then gradually decreased until reaching a low mean squared error value of 0.0099739. The training process goes through 262 epochs can be considered acceptable number of iterations. As we see, we have two figures, figure 6 and figure 7. Figure 6, the error histogram during the training phase. Actually, this figure illustrates the relationship between the number of histogram instances and error. It yields that there is a nice result distribution around the zero error. It looks as a normalized Gaussian distribution. But the figure 7 provides the regression result of the CBRN training phase. The regression performance, which is given in this figure, represents the relationship between the targets and output of the CBRNN. Significantly, the regression parameter R reveals a very high value of 0.97984. This means that the regression is so successful as the best R value is 1. For the testing phase, the final CBRNN training weights are used. It can be investigated that the output of the CBRN are affected by the Bayesian regularization. This yields a big advantage of providing a highly regular output value. In addition, using the Cascade forward neural network has the importance of directly connected between the input and output value through effective weights. It's a pleasure to reveal or to discover that the testing phase of our CBRNN benchmarks a low mean square error of 0.0219. For the case of compression, the proposed cascade Bayesian generalization neural network has been compared with other neural networks for the purposes. These are the radial basis function neural networks, element neural networks, multiple positron probabilistic neural networks, momentum cascade forward neural network, and MLP with adaptive learning rate, able to shows mean square error testing cooperation between different neural networks. From this table, it can clearly be seen that our proposed CBRNN has outperformed and surpassed other neural networks. That is, the proposed CBRNN has achieved the lowest testing error of mean square error with 0.0219, whereas other compared neural networks have shown far mean square error values for the testing phase. In this paper, the Cascade Bayesian regularization neural network was proposed. It's employed successfully and accurately, identifying issues as faults for a determined electrical circuit. The CPRNN uses the lines, currents, and voltage as inputs, and the ground and phases as outputs. It also has a single hidden layer, so it's a multiple layer neural network. It's a pleasure to highlight that our proposed CPRN has obtained a very low testing error of mean square error with 0.0219. Moreover, Our work or our network has been compared with other neural networks and it showed better performance. It's essentially outperformance and surpassing the compared neural networks. To summarize the key finding more comprehensively, agent organization could effectively influence performance of the Cascade forward neural network, composite RNN, and this is due to its analyze capability. For future research or practical applications, electrical infrastructure management, the CBRNN can be implemented for other electrical circuit and investigated for more type of faults.